Yo, what's up guys? Welcome back to another super exciting installment of Finite Element Methods. So as promised, I'm going to finish up the example that I did in my last video where we have this three-member truss system and we solve for the displacements at node 3 using the stiffness matrix method. So we found the stiffness matrices for each element. We've got our first element, second, and our third, and we solve for the displacements at node number 3 because we've got a pin at node 1, a pin at node 2, and a fixed support at node 3. So there's only going to be movement at node 3, and we solve for those. In the x direction was 3.47 times 10 to the minus 3 meters, and in the y direction negative 1.32 times 10 to the minus 3. So what we're going to do now, we're going to solve for the forces within each one of these members, and then that'll basically wrap up the problem, and that's pretty much 100% solved. So let's do it. Okay, so if you recall, we'll start off by just looking at our local stiffness matrices, and we'll write down each one. So K1. So there's our K1. It's symmetric, so I'm not going to fill in the rest. So now what we want to do, we want to solve for the internal forces at member number 1. Alright, so if we remember, each node is going to have an x component and a y component, and I'm going to label these fx, f1x due to member 1, and f1y due to member 1. And then if we're looking at the third node, we're standing at the third node looking down to our first node. We know there's going to also be, actually let's erase these forces just for now so we can get a better understanding of what's going on here. Alright, so now there's also going to be, I'm just making these directions arbitrary, but we just know there's going to be a 3y due to 1 and an f3x due to 1 as well. Okay, so we can find those forces, those internal forces, and take the magnitude to get the overall member force. Alright, so we're going to do that for each member. So just remember, I've labeled these in the negative direction. Doesn't mean that they're necessarily going to be in the negative direction. I'm not going to put them negative in my matrix. I'm just showing you for illustrative purposes that these components will be due to the third node in the first member. Okay, so in order to write this out, it'll make more sense. If we recall that we have our force vector equal K times our displacement vector. So we found our displacement vector. Remember, we got U1, or U3x and U3y, right? So we can fill that in by saying, remember we have our F1x due to the first member, F1y, first member, F3x, first member, F3y due to the first member. Just like when we're doing the one-dimensional problems, we label it such that we can just keep track of everything, right? We have our node 3 due to the first member, so that's how I'm labeling this. Label it how you want, just as long as you keep track of everything. And that's going to be AE over 50 multiplied by our stiffness matrix K1. I'm not going to fill it in quite yet, I'll show you why. Because now remember, we got our U1x, U1y, U3x, U3y, because remember, we're dealing with the U1x slot, U1y slot, U3x, U3y slot. Because if you look back at our stiffness matrix for the first node, or the first stiffness matrix for the first member, you'll see here that we're dealing with our 1 and 1, 3 and 3. Okay? So same thing for this, exactly the same thing. We're using the same stiffness matrix, and then we know that, okay, that's equal to 0. U1 of x is equal to 0. U1 of y is also equal to 0, because if you remember, we got a pin support. We're not going to allow any movement. So we're only going to allow movement at the node 3, which we have already solved for those displacements. So now if you remember from the first, or for the 1D problems, we can cross out this entire row because that's 0 now, right? So we can kind of just cross it out and as well as the first and second columns, because we want to make it a square matrix. So right now all we're looking at is the third row and the fourth row and the third column and the fourth column, right? So that gave us a 2 by 2 matrix, which is perfect. So let's fill this in, and if we look back up to our stiffness matrix, we got 0.36 and 4.8, right? Because I got these directly from our stiffness matrix K1, which is easy, right? You get that. All right, so now it's exactly the same thing, guys, as the one-dimensional problem. Literally all we got to do is matrix multiplication. We're looking at the first row. We're looking at the first row, matrix multiplication, first row, right? So we could say f3x due to the first member is equal to AE over 50. That is the first component in the x direction force. So let's quickly calculate that out. Now, same problem, so if you remember the values, the area, 200 GPa, right? So do this calculation, and we get a force due to the first member at node 3 in the x direction is equal to 12.3 kilonewtons. All right, so that's the first component that we need to deal with, okay? And now F3 of y, now we're looking at the y direction, first member, looking at the y direction, so we're looking at this row, and then we're still multiplying by our displacement vector. So that is equal to the same area, same length, same modulus of elasticity, but now we're dealing with, remember we're looking at the 0.48, that's times our U3x plus 0.64, just remember this is 0.64. That is multiplied by our U3y. So every time we're dealing with a specific member, remember you always got to go back to that same member's local stiffness matrix, right? We did calculate the global stiffness matrix, but now we're just solving for the internal forces in the member, in member 1. So we're dealing with local stiffness matrix number 1, right? And then we're breaking it down into all of its force components, and we're just picking out which part we want to solve for. We're looking at F3 of x and F3 of y because we've got displacements in 3x and 3y. So therefore, if we plug in U3x and U3y as our values that we've solved, I'm not going to rewrite this out because it'll just waste time. Then we're going to get a F3y due to member 1 of 16.42 kilonewtons, right? Okay, so now all we've done with this, if you look back at our original picture, we've solved for this and for this, but we want to find the force within the member, okay? So we need to take the magnitude. We got to take the magnitude of these, right? So we'll say F member 1 is equal to, we're going to take magnitude is easy, just square root 42 squared plus, for the force in member 1 is equal to 20.5 kilonewtons. And that's it. That's the answer for the first member. So we got F1 of 20.5 kilonewtons.